How's it going, folks? Welcome to Diff Calc. This is week 6, video 1. Today we're going to be looking at applications of minimums and maximums. This is otherwise known as optimization. Let's go ahead and get started. So I'm going to pose a question here to start. You have 58 feet of fencing that will be used to create a rectangular border. What should the dimensions of the enclosed area be to maximize this area? So we have 58 feet, and it's going to create a rectangular border. What do you think the dimensions of this enclosed area to maximize its area should be? So how can we use what we've been doing, finding relative mins and maximums, in real applications like the example prior? Tell me what you think. So let's look at another example here. A manufacturer wants to design an open box having a square base and a surface area of 108 square inches. What dimensions will produce a box with maximum volume? So using optimization, we're going to be able to solve this. We're going to start off by identifying what we're looking for, which in this case is our maximum volume. Now our volume in this case will be x times x, which is the base because it's a square base, times h, given the variables in this drawing here. So since this is what we're trying to optimize, this equation is going to be known as our primary equation. Okay, this is super important. This is our primary equation. This is what we are essentially trying to find its maximum or minimum given a certain situation. Now, in a lot of problems like this, we're going to be given extra information. In this case, we're told the surface area has to be 108 square inches. So we're going to set the surface area equation, which in this case will be x squared, which is the area of the base, plus 4x times h, which will be the area of the sides. We do not have to factor in the top because it is an open box. And we know that the surface area is equal to 108 from the given information. Now, we are not trying to optimize our surface area. It is a restriction for our volume. So since it's a restriction, this is going to be known as a secondary equation. Secondary equations are what we're going to use to be able to get our primary equation in terms of one variable. Okay, we're essentially trying to turn this primary equation into terms of one variable, and we're going to manipulate our restriction or our secondary equation to do so. Now I'm going to go ahead and solve my surface area here for h. So that way I can replace this and get it all in terms of x. So from here, I'm going to subtract x squared. I'm going to have 4xh is equal to 108 minus x squared, and I'm going to divide by 4x. So I'll get h is equal to 108 minus x squared over 4x. So now that I have my h in terms of x, I'm going to take this and plug it into my primary equation. So my new volume will be x squared times 108 minus x squared all over 4x. And when I simplify this, I'll be left with 27x minus x cubed over 4. So this is going to represent the volume given our constraint of surface area. So this function here will represent the volume of this box given the constraint of the surface area. And from here, we're just going to use the either first derivative test or the second derivative test in order to find our relative max. Okay. Also, something you want to keep in mind is something called a feasible domain. A feasible domain are all the realistic values of x. So in this case, x can realistically be any number that's larger than 0. Okay, we can't have a side of a box be 0 or be a negative value. So all of our realistic values in this domain will be greater than 0. So taking our volume function, we're going to find our relative maximum. I'm going to go ahead and use the first derivative test. So I've got my volume is equal to negative x cubed over 4 plus 27x, just putting that in standard form. That's not the derivative yet, that's just my volume. Then I'm going to take my derivative, and my derivative function is going to be negative 3x squared over 4 plus 27. I'm then going to find my critical numbers, so I'm going to set my derivative equal to 0. I'm going to go ahead and get that 27 is equal to 3x squared over 4, and then I'm going to solve for x. From here, I'll get that 108 is equal to 3x squared. From here, I'll get that 36 is equal to x squared. And I'm going to get that my critical numbers are going to be plus or minus 6. Now, only one of these are going to represent a critical number because the other is not part of the feasible domain. So we're not going to include -6. We're going to say that our critical number, we're only going to have one of them, will be positive 6. Okay, so at x equals 6, we will find our relative max just to make sure using our first derivative test. We're going to have our critical number be 6. Anything to the left of it will be positive. Anything to the right will be negative. And as we can see, the function is increasing from 0 to 6 and decreasing from 6 to infinity. So we will have a relative maximum at 6. So we want our relative max to be 6. Okay, so since we know that we're going to have a relative maximum when x is equal to 6, we now just need to find the height or the actual volume, which is what we're looking for. No, we're just looking for the dimensions. So let's go ahead and set up our surface area function. So we know that 108, which is our surface area, is equal to x squared. We know x is going to be 6 plus 4 times 6 times our height. Our height is the last piece of information we're looking for. When we work this all out, we're going to find that our height is equal to 3. So our dimensions that maximize the volume will be 6 by 6 by 3 inches. Okay, and this is what we are essentially looking for as a final answer. Now, just some guidelines for solving applied minimum and maximum problems. We're going to identify all our given quantities and quantities to be determined. Okay, this is essentially going to be our given quantities are going to be our restrictions or our secondary equations. And our quantities to be determined will be our primary equations. These are what are going to be optimized. Okay, from here, we're going to write our primary equation for the quantity that is being maximized or minimized. We're going to change the primary equation, so that is in terms of one variable. A secondary equation may be needed in this case. We're going to then determine a feasible domain for the primary equation, what will actually make sense for this problem. And then finally, we're going to determine the desired maximum or minimum using either our first or second derivative test. And that's all I have for today, folks. Thank you very much.